Okay, so we were just discussing how the first part of the fundamental theorem of calculus that says g of x equals the integral from t equals 0 to x of f of t dt, that can be viewed as the area under the curve. So let's do an example where we're actually going to apply it that way. Example, we'll use capital F instead of capital G now. Let capital F of x equal this funky function that's defined in the fundamental theorem. It's the integral from t equals 0 to x of f of t dt, where f is actually the function that's pictured in the sketch. It's very angular. You see it starts down there at -2 on the y-axis, and then it passes through 1 on the x-axis, up to 3 level on the y-axis, back down to 3 on the x-axis, up to 1 level at x equals 4, and then back down to 0 at x equals 5. That's the function f. Now, with that picture, they want us to find part A, capital F evaluated at 0, capital F evaluated at 1, evaluated at 3, and evaluated at 5. Part B, find the x-intercept upon which, the x-interval upon which the capital F function is increasing. Not the little f, not the picture that you see there, but the capital F. The capital F for which we found the points in part A. Part C, the question is, where does capital F have a max value? And part D, do a sketch of capital F of x. Okay, let's try to answer these questions. Solution, part A, capital F of 0. Well, according to the definition, it equals t from 0 to 0 f of t dt. Well, that's just equal to 0. Go back and read note number 110, rule number 2. When you take an integral and the bottom limit number and the top limit number are the same, then the answer will be 0. All right, what's capital F of 1? Well, geometrically, that's defined as that negative area between the function and the x-axis. So that's this right triangle with height 2 and base 1. So it's 1/2 the base times the height. And you can see here that we're going to go ahead and color these in. But anyway, back to the f of 1. F of 1 is negative the 1/2 times base times height, the formula for the area of that triangle. And that simplifies to -1. So f of 1 is equal to -1. And you see what we did to the graph? We shaded in that first area and the others also. And we put a negative sign to indicate because that area is below the x-axis, we consider that a negative area. Because in a moment, we're going to be combining these. And we have to remember which ones are negative and which ones are positive. Okay, let us continue answering part A. What is capital F evaluated at 3? Well, it's the area of the first triangle, so it's the thing that we found for f of 1, and that's negative, plus the positive area from x equals 1 to x equals 3. That has a base of the triangle 3, base 2, height 3, so that's 1/2 base times height, and then you combine that with the first part and you get 2. So f of 3 equals 2. F of 5, well, go back and take negative area of the low triangle plus the area of the larger upper triangle, and now add the area of the last triangle, which has a base that's 2 units long and a height that's 1 unit high. So that's the -1 for the first part, plus 3 from the second part, and now the area 1/2 base times height, which simplifies to 2 plus 1, it's equal to 3. So f of 5 is equal to 3. And just a summary of what we just found for part A. Thus, we have ordered pair points on the graph of capital F of x, not little f, that's what's in the picture. We found points that are in capital F of x. They're the ordered pairs xy equals 0, 0, 1, -1, 3, 2, and 5, 3. We're going to use that to answer the rest of the questions. Okay, let's go to part B, where we're asked to find the x-interval upon which the function capital F is increasing. It looks like capital F is increasing on the x-interval from 1 to 5. If you just look at the ordered pairs, it appears that it keeps growing and growing, so it's getting larger and larger as far as the Y partners in the ordered pairs. And part C, where does the function capital F have a max value? That appears to be at x equals 5 because the value, in other words, the Y partner to x equal 5 for capital F is the value 3, and that's the largest Y value in the group. And part D, we're going to sketch the points that we derived in part A. Well, we have a point at 0, 0, 1, -1, 3, 2, and 5, 3. I'm not going for perfect accuracy, but I'm just going to go ahead and plot these points and connect them together in some kind of a smooth curve. And then we're going to look at it for a moment. I'm going to freeze this thing and we're going to think about it. Okay. So let's compare capital F graph that we just drew to the graph upstairs that we're given of little f. Now remember, this is not very accurate. Our capital F is not very accurate, but one thing I do notice, one very important detail, up in the original given graph of lowercase f, there was a root, a 0 at x equal 1. Look what that translates into in the picture of capital F of x. It's a low point on the graph. It's a point of inflection. Well, not inflection because it's not changing concavity, but it's a minimum point there. That sure sounds familiar. That sounds like something we used to work on before. But I won't let the cat out of the bag. We'll learn about that later.